Hello and welcome to my YouTube channel. Today I'll be talking about Norton's theorem. I've already talked about Thevenin's theorem and superposition theorem. You can go and watch those videos if you are interested in understanding those theorems as well. Now, when it comes to Norton's theorem, here again, I have a circuit diagram. This is just to give an explanation on Norton's theorem. Now, what Norton's theorem says is that a linear active circuit can be replaced by a current source in parallel with a resistor. Right? That current source is referred to as Norton's current. So we have Norton's current. And the resistance is also called Norton's equivalent resistance. And Norton's equivalent resistance is just the same as RTH, right? It's just the same as Thevenin's equivalent resistance. Now, how do we determine our linear active circuit? Because we can only replace a linear active circuit with an equivalent circuit, right? That is a current source in parallel with a resistor. Now, when it comes to a linear circuit, you can think about it this way, right? You can think about having a battery, right? And you're trying to connect the battery to a light bulb. Then you factor in the fact that the battery is having a internal resistance. And maybe you connected the first time the battery to the light bulb. It lights up for some time, but the brightness started to reduce. So you add the current source to boost the brightness of the load, which is the light bulb, right? And then this is also trying to consider the fact that the current source is the 2 amps, which is the current source, is also having some internal resistance as well. So this is just an example. Now, the light bulb in this case is our load, because it's an important component in the circuit diagram, because it's taking the current from the 1.5 volts and the 2 amps, and then it lights up the bulb, right? And the bulb will now lights up. Now, what we do next is that we look at the circuit diagram. We try to separate the load from the rest of the circuit diagram. So we have our load and then unload part. Then the unload part of the circuit diagram is what we refer to as linear active circuits, right? Linear active circuits. Now, the linear active circuit part is what we have to convert to a current in parallel with the resistor. That current source is referred to as what? Norton's current. Now, Norton's current, IN, is the short circuit current, all right? And then Norton's equivalent resistance is the equivalent resistance when all independent sources are turned off. Now, how do we determine the Norton's current, which is the short circuit current? What that means is that once you are given your circuit diagram and you've been able to identify your load in the circuit diagram, you come and short circuit the load, right? What that means, you connect a wire parallel to the load resistor. So I can come here, connect a wire to this wire. By connecting the wire, because the wire is having a very small resistance relative to the load resistor that I have here, that means all the current will tend to pass through the wire, because current passes through the least resistive part of the circuit, right? So you can see the wires, it has a very small resistance. Why? Because the wire that we tend to have, they tend to cover copper wires. And copper, the resistivity of copper is very small. It's about 1.72 times 10 to the power minus. And resistance being directly proportional to resistivity of the copper it means the resistance is also going to be smaller, very small as well. So it short circuit the load. So now, since all the current will pass through the the wire, we can remove the load resistor, and then we get such a circuit diagram. So the current in the wire is what we refer to as the short circuit current, which is the same as what? The notice current. Now, once we've done this, you just go ahead and solve for the current, the notice current in the circuit diagram, and then will give you what? Your notice current. Then when it comes to that notice equivalent resistance, is the equivalent resistance when all independent sources are turned off. So here, I will remove the wire, right? So that I have my linear active circuit. Then I'll turn off all independent sources. So I have this and a voltage source. You turn it on by connecting a wire. Then when you come to the current source, here is being turned off by removing the current so that it will be open. And then here you can see that I have only resistors. So I have 0.5 and then 1 ohm resistor. Right? You can see here the two resistors are connected in parallel. And then the equivalent resistance there will give me the what? The notice equivalent resistance. Okay. So I'm going to be providing an example. So see you in the next video. Now we are going to look at an example. So we have a circuit diagram here. We are asked to find the current passing through the load resistor. Okay. And this is our load resistor. Now, I'm going to be using Norton's theorem to try and then solve for the current passing through the load resistor. And since we can see the load resistor in the circuit diagram, what that means is that when it comes to Norton theorem, we know that Norton's equivalent circuit consists of what? A current source and parallel with a resistor, which is Rn. So we have In in parallel with what? Rn. So that is the equivalent circuit. So we have to first get In and Rn. And in getting In, which is a notice current, is the short circuit current. Well, that means we come to our load and then short circuit the load. I'm going to short circuit by connecting a wire. Once I've connected the wire, then I can eliminate the load resistance because all the current will pass through the wire. Right. Now the current in that wire is the notice current. Now I just go ahead and try to find the current. You see that current that is passing through the wire is going to be the current that is passing through the resistor R3 here. Now how do I get that current? Here I just have one voltage source and then resistors. That means I can use network reduction method. So using network reduction method, I can first get the equivalent resistance of the circuit diagram. And that is going to be R3 and R2 are connected in parallel, and the AC is what? R1. So that will be the product of this over the sum plus R1, which is here. Now that I've gotten the equivalent resistance, which is the overall equivalent resistance for this circuit diagram, that means I can get the main current I, which is going to what? The voltage source over the equivalent resistance. Then from there, based on what? Now, current divided rule, I can find the current passing through what? The Y, which is the percent of the current passing through R3. And that will give me, since I'm choosing the current passing through the wire, so if you take the other resistor, and then that was 2 over R plus 2 times what the current, so that will give me the notice current. Now we go to what? RTH. RTH is the equivalent resistance when all independent sources are turned off. As you can see, I have one voltage source and I'm going to turn it off. So by connecting a wire, Then, but before you do this, you have to make sure you remove the wire so that you have your linear active circuit, right? You remove the wire, and by doing that, you get this kind of circuit diagram, right? And then the equivalent resistance, as you can clearly see, R1 and R2 are connected in parallel. So that's the product R1 times R2 over the sum R1 plus R2. Then after that, the IC is what? R3, so plus R3. Now that I've gotten my IN and Rn, right? I've gotten IN and Rn, then I'll connect the load resistor, then use current divider rule to find out the current passing through the load resistor. Because as you can see there, IN here is the total current, and then Rn and the load resistor are connected in parallel. So we use current divider rule, and this is what we get. Make sure you subscribe and then like the videos. That will encourage me to make more videos regarding circuit diagram, and then share the link with your friends and your colleagues so that they also benefit from this explanation. Bye-bye.